We're going to jump right back in where we left off. Last time we were looking at section 1.1, mathematics and problem solving. And we had done two examples, but they were kind of very similar, right? Like they were a method called Gauss's method, or what we sort of affectionately call Gauss's method. We took his example that happened real life to him when he was young, and then we used it to solve a similar problem to that. And it was kind of a pattern approach looking at how numbers were added together. And so it was these problems right here. That was Gauss's actual problem, and then this was the similar related problem. So we're going to look at several other strategies today as well of problem solving. All right, so here is our next example. If a soccer league has 10 teams and each team plays every other team once, how many games will the league manager need to schedule at the start of the season? Super practical. You would need to know this if you were creating schedules for the teams. Cannot tell you how many times I have been to somewhere that somebody is not able to create one like this very well. It's a problem. You'd also need to know this for, in this particular situation, like for referees, for hiring and things like that. So, as we're taking a look at this example, the 10 teams makes it a difficult problem. But if we simplify the number of teams, it's easier to see what's happening and then how to generalize it back to the 10 teams that we started with. So what we're going to do is we're going to consider what would happen if we had 3 teams. And just for the ease of doing this, we're going to call the teams just the letters A, B, and C, okay? So I'm going to start by just listing all of the games that would be necessary. So Team A has to play Team B, and Team A has to play Team C. Team B has to play Team A, and Team B has to play Team C. C has to play A, and C has to play B. So it kind of looks like there are 6 games. But are there? No. Some of these games are repeats. In fact, half of them are, right? So once I wrote down BA, that was a duplicate because I already had BA written down. And when I wrote down CA, that was a duplicate in CB. So I ended up with half the number that I wrote down, right? Half the number of games. So where do you think that we might have come up with 6? Why would it have been 6 considering that we have 3 teams? Any ideas?
What do you mean?
So I'm trying to find a pattern that says if I have 10 teams, how many games do I have? So originally, on this, the way I changed it, we had 3 teams and there were 6 games. And then I noticed that half of them were doubling, right? But where do you get, what would I do for 10 teams without writing out all of these numbers? Because our letters are combinations of things. Where did the 6 games come from?
So 3 times.
It's 3 times 2. Yeah, why is it 3 times 2? Because there's 2 other teams. Good. Okay, so there are 3 teams times 2 games per team. That's why we originally had 6 games, right? 2 games for A, 2 games for B, 2 games for C. That's where the 6 came from. But when I did that, I ended up double counting everything, of course. So after I did my 3 teams times my 2 games, in order to remove the double counts, what would I do? I would divide by 2. That should make sense. I have 3 teams. Each team plays 2 games. But if I count all of those, I counted every game twice because I counted them for Team A and I counted them for Team B, right? So the AB was written down twice, and it happened for every game. So what would I need to do if I'm thinking of that mindset for my 10 teams? Yeah, it would have 10 teams each playing 9 games, right? If they play every other team, they'd play 9 games. But this will actually be double the games because it would have counted everything twice. So I would need to divide by 2 to remove the double counting that happens. What is 10 times 9? 90, and 90 divided by 2? 45. So there are 45 games that must be scheduled in this league. Does that make sense? If you can simplify the problem down to fewer cases, or fewer, in this case, numbers of teams, it's easier to see what's actually happening to find that. Because I don't know about you, but I don't want to have letters A through whatever, 10 letters, and try to combination that with every single one. There's going to be 90 of them. I don't want to do that. And it's going to be really hard to find out that it's exactly double counted if I have that many of them to look at as well. So if I simplify the case down to a smaller number of teams, it's easier to see that everything's double counted and that I end up with double the number of teams and so forth, or double the number of games and so forth. All right, let's try another one. I think this one's an interesting one. Not that screen. There we go. A store sells bicycles and tricycles. There are a total of 15 cycles, when you include both, in the store. There are a total of 35 wheels on those cycles. How many of each type of cycle are in the store? So every time I read this one, and probably most of you are doing this too, you think of stuff you did in high school. X is bicycles, Y is tricycles, and I create a couple of equations, and there's 2 unknowns, and I have to solve. Did you guys think that? Yeah. That's what it looks like. It looks like that kind of a problem. But there's really no need for us to create equations. I mentioned that on Monday, that sometimes we can do equations, and if you do equations here and solve it, that's okay. But the point is to do the problems where we don't need high school level mathematics, because this problem can be done by much younger students. So I'm going to show you an example of one with this one where you can make a diagram, and maybe you wouldn't have thought to make a diagram of such a thing. But we know that there are 15 cycles, that's a weird word, but cycles in the store, right? And they have at least how many wheels on each of them? 2. So what I'm going to draw is my version of a cycle. It's terrible, but it gets you the image. That's a cycle with 2 wheels. You good with that? And I'm going to draw 15 of these. So I want you to draw 15 of them as well. I'm going to cheat and copy paste. So right now, I have satisfied the 15 cycles in my picture. How many wheels do I currently have? There's 30. It's 15 times 2. Some of you are counting them up. That's okay. There's 30 wheels. How many wheels am I supposed to have? 35. So what do I need to do? Add 5 wheels by making some of them tricycles. You got it. So pick which ones you want to be a tricycle and just add a wheel. There's 1, 2, 3, 4, and 5. We're done. We need to answer the question still. But how many of each do we have? How many bikes are there? 10. And how many trikes are there? 5. And X and Y were not necessary. Okay, that's pretty cool now, right? It's pretty cool. There's an example in your book that you're going to see that's going to have this very same feel to it when you get there. Just remember, If you can draw pictures to help you solve problems, it's often a much easier approach than working with actual algebra, okay? All right, guess and check. Told you last time this was a valid method, and some of your eyes got big. Like, seriously? You've got to be kidding me. I've always been told that's terrible. It's not terrible. Here we go. We have 48 feet of fencing, and we wish to make an enclosure along one side of an existing barn. What lengths would the sides need to be to have the greatest area enclosed for our chickens? So, the first thing I would suggest is that we do make a portion of this as a drawing. It's talking about a physical object, right? A barn. So let's just draw a barn. There's my barn. Okay? And we're going to make a fence with the barn as one of the sides of the fence. If any of you have fences at your home, you don't fence along the house itself, right? It would be a waste of your material. So whatever fencing material you're using, you don't actually put it right next to the side of your enclosure or of your building, or your structure. So if I'm making a fence for my chickens, it would only actually have 3 sides. So far, so good. Okay? What can you tell me about the sides of this enclosure? There's one thing you know for sure. 2 of the sides are equal. Yeah. This one and this one are the same. You've got a rectangular enclosure, right? 2 sides are the same. So whatever I decide for the top, it's going to have to match for the bottom. The other thing that you know about this enclosure is that it's a total of 48 feet. And we're going to use all of it, because if I only use 45, then clearly it could have been made bigger, right? So I don't want to use less fence than I've actually got to use. No leftovers. So we're going to use guess and check. I already do a drawing, so this has kind of got that drawing aspect to it as well. And we're going to do it in an organized way so that as I guess and check, I have a record of what I've done. If you're not keeping a record of what you've done, then it's really difficult to make our next best educated guess without just kind of being all over the place. So the things that I need to know is I need to know what my side lengths are. And I need to know what the area is. Because the goal is to have the biggest area possible. So remind me what you know. What is the area for a rectangle? I'm not trying to confuse you, just asking for you to give it to me. Y'all know it. Area of a rectangle. Thank you. You're all like, oh yeah, I knew that too. Length times width, of course you do. Length times width. So whatever side lengths we get, the length times the width is going to be the area for my enclosure. All right, so I'm going to give you the first guess. So I'm going to guess one side length is 10, and I'm going to always give you the side length, or you're going to always give me, let's just start with the side length that's shorter, and then figure out what the longer one would have to be. So if the top one's 10, the bottom one's also 10, so how much is left for the long side? 28. Yeah, so I've got 10, 10, and 28. So this would be like this. So when I do my area, what would my area be? 280. And it's square feet because I'm multiplying feet times feet. Okay? Now, if I only have one guess, I have no way of knowing if I might have accidentally guessed the right answer to start with. Like, it's possible. You might actually do that. But if all you show me is one thing and it happens to be the right guess, you still didn't show me sufficient work to for sure know that that was the right guess. Do you know what I'm saying? You got to show me some wrong guesses too to verify that your guess itself, whichever one it was, is actually correct. So we're going to manipulate this by changing now this number at the top. So instead of a 10, I'd like for you guys to give me another number to put on the top of my rectangle. 15. Okay, so if the top is 15, what else do I know? Bottom's 15. So that's a total of 30, right? Which leaves how many left over? 18. So I'd have 18 over here. So one possibility is I have 15, 15, 18. Whoops. So if I multiply 15 times 18, that would be my area. I don't have that one written down, so somebody's going to have to do it for me. What's 15 times 18? Calculators in class are a really good thing. What is it? 270. So right now, my first guess is better than my second one. But it still doesn't mean it's the best one, right? So let's try something else. Change again the number on the top. What would you like to guess? 5. All right. 5 on top makes 5 on bottom. That's 10 total. What's left? 38. Okay, so I've got 5, 5, 38. What is 5 times 38? 190. How much? 190. Is that what I heard? I don't know. I don't have that one written down either. Is it 190? That sounds right. Sounds right. Yeah. Okay, so again, so far, my first guess is my best guess. It kind of feels like the further away I'm getting from 10, maybe the less of a good guess it is. But I've gone pretty far away from 10 each time, right? I mean, I've gone 5 away. What if I go a little closer to 10? Can you give me another example? 9. Okay, so let's try 9. So 9 on top, 9 on bottom makes 18, leaving me with what? 30, I think. Yeah, 30. Yeah, okay, so 9, 9, and 30. So what's 9 times 30? 270. Okay, so here's the deal. I know that everything that I'm getting between 5 and 9 are going to be between the 190 and the 270. Does that make sense? And that's less than the 280 I already have. So I don't need to guess anything else between 9 and 5, okay? But I might want to guess something still between 10 and 15. So let's try another one. Tell me a number between 10 and 15 for the top. 13. So 13 on top and bottom is 26. So what would that give me for my third side? 22. All right, what is 13 times 22? Ooh, 286. And I've got a new front runner as a possibility, right? Okay, but still, like 13 is between 10 and 15. So I still don't know that it's the best answer. It's just better than the 10 or the 15. So I need to guess some more numbers. What else might I guess? 12? Okay, so let's go with 12 on the top and bottom. So I have 12, 12, and what? 24. Ooh, 288. That's even a little bit better. Now it's kind of hard to see because we've jumped around a little bit, but let me take a look with you and to notice this. I'm just going to put them in order. I tried 5, 9, 10, 12, 13, and 15 so far. Everybody with me? I'm not going to write the other parts of it out. I'm just putting them in order. So with 5, I got 190. 9 gave me 270. 10 was 280. 12 is 288. And then I've got 284. And then I've got 270 again. So if there is a better guess, I mean, I've kind of, you know, from 12 down to up to 13, it gets smaller. And then from 13 to 15, it gets even smaller. If there's a better guess, it's got to be in between the 10 and the 12, right? And it may or may not be a better guess, but we got to check because it might be. So we're going to check our last possibility is 11. And if it's not any better, then 12, 12, 24 is my best choice of the others I've tried. All right, so what is 11, 11? Gives me 22. How much is left? 26. So what is 11 times 26? Yeah, it's 286. Yeah, just like the 13, 13, 22. So the best answer actually ended up being the last one we did before that, 12, 12, 24. And we need to make sure we answer the question that's asked. We've done all the work for it now. We just need to answer the question. It says, what lengths would the sides need to be to have the greatest area? Well, they would need to be 12 feet, 12 feet, and 24 feet. Make sense? Keeping track of our values helps us with that. Any questions on that one? That's required probably the most work so far of any of the problems we've done. Okay, the next one's a fun one. One winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. What was the temperature at midnight? So this is actually a really good example of working backwards because what you know is the final result. The end result is 32 degrees, freezing. And you're trying to figure out what happened at the beginning. Okay? So what might be a good thing to do to start out with? How might you start this problem? Some of you are already starting it, so tell me what you're doing. What'd you do?
I did 32 minus 10 degrees.
Okay, so you started at the end and you're working your way backwards, right? Okay, and I agree with you. I think it might be helpful for us to just write down the numbers of the times we're talking about so that we can figure out where we're going backwards to in order. Does that sound okay? So we start at, was it 9 or midnight? We start at midnight. What's the time after midnight, the next time they reference? 5 a.m. And then after 5 a.m.? 9 a.m. And then noon. Okay, so midnight to noon. We know that at noon it ends up being 32 degrees as our final temperature. And we've got a description of how it changes as we work our way along. What happened between midnight and 5? It went down 15. What happened between 5 and 9? It doubled. And then what happened between 9 and noon? Yeah, it went up 10. So that's what's happening in a forward progression, right? From the earliest time to the last time. So as we go backward, we're going to do exactly what you said, is that we're going to we're going to subtract 10 to go backwards. So we're going backwards now. So if it's at 32 at noon, what would it have been at 9? 22, right? And if it doubled from 5 to 9, what would it have been at 5? It would have been 11. And if it went down 15 to get to 11, what would it have been at midnight? 26. So we have a 26 degree temperature at midnight. Make sure that you're showing me what the answer is somewhere. So box it in, circle it in, highlight it with a color. I don't care what you do, but make sure it's obvious the answer to the question, okay? All right. The last thing that I want to show you is a reminder of the 12 days of Christmas, along with the religious symbolism that you may or may not have ever heard behind the 12 days of Christmas. There's a question in your book about the 12 days of Christmas, and I don't know about you, but once we get about past 7th day, I start forgetting which item it is that I add on each day, unless I'm being really careful. So I want to make sure you had that as well. Okay, so the first day of Christmas, the partridge in a pear tree, represents the number 1 represents true love, which is God. 2 is 2 turtle doves. The 2 turtle doves represent the Old and New Testament. 3 French hens on day 3, faith, hope, and love. The 4 calling birds are the 4 Gospels. The 5 golden rings are the Pentateuch. The Pentateuch is the first 5 books of the Old Testament. The 6 geese a-laying are the 6 days of creation. The 7 swans a-swimming are the 7 gifts of the Holy Spirit. 8 maids a-milking are the 8 Beatitudes. 9 ladies dancing are the 9 fruits of the Holy Spirit. 10 lords a-leaping is the 10 commandments. 11 pipers piping is the 11 faithful apostles. And then the 12 drummers drumming is the 12 points of doctrine in the Apostles' Creed. So it's kind of a cool symbolism that's actually within our 12 Days of Christmas fun song. The other thing that I wanted to mention is that every time I have a group of students that gets to this problem, there are some students who don't really understand how the 12 Days of Christmas works. For example, if I were to ask you, how many turtle doves do you get? Well, you get 2 turtle doves, but you get them on day 2, and you get them on day 3, and you get them on day 4, and you get them on day 5. Do you know what I'm saying? Right, so when you get to day 10, you have 10 lords a-leaping, 9 ladies dancing, 8 maids a-milk. You get all of those things on day 10. So you don't just get 2 turtle doves on day 2. You get 2 turtle doves on day 2 and every day that follows, which means you get them for 11 days. You get 22 turtle doves. Are you with me? There's always a misconception in the way, I don't know if it's the way the problem's worded or what exactly. All right, so we're going to do group work next.